Welcome back. In my earlier video, I have told you do meditation in every morning. And today I will say what is meditation. Meditation is a simple technique to make your mind calm to every situation and re-energize and regenerate your mind. It helps to focus in your every work, and meditation keep our body too healthy. Seem like bath. Some people think meditation means some religious concept, but actually this is no. I will tell you some technique of meditation. When you get up in morning, try to say thank you for everything. Thank you for your beautiful life. Thank you for your home, and thank you for your family and all others things what you achieve. And just close your eyes and try to take deep breath in positive energy, happiness, joy and love, and breathe out all negative energy. Many thoughts will come in our mind, but don't try to stop it. Don't try to avoid it, because mind is very naughty. Try to do such meditation. It obviously helps you to focus your work in positive way. Just try. In my earlier video, I had discussed about maximal ideal of C01. Today I will discuss prime ideals of C01. First I will see some question of prime ideal of C01. First question had come N.b.h.m PhD exam 2018. The question is, which of the following are prime ideal in the ring C01? Option 1, J equal to set of all f in C01 such that f of x equal to 0 for the interval 1/3 less than equal to x less than equal to 2/3. At first, see the first option, then I will discuss the second and third option. Here fx equal to 0 in the interval 1/3 less than equal to x less than equal to 2/3. And at first recall definition of prime ideal. If RBI doing an ideal P is said to be prime ideal if non-zero AB belongs to R such that AB belongs to P imply either A belongs to P or B belongs to P. Here the interval x lies between close interval 1/3 to 2/3. So at first divide 0, 1 in the interval, here 1/3, here 2/3 and here half. And for this interval consider a function such that fx equal to 0 in the interval 0 to half, means in this interval the value of the fx is 0, and half less than equal to x less than 1, the value of the function is x minus half, and gx equal to x minus half for 0 less than equal to x less than half, and 0 in the interval half less than equal to x less than equal to 2/3. Here the value of the g is 0, and other interval means 2/3 less than equal to x less than equal to 1, the value of gx would be considered as x minus 2/3. Here notice in the interval 1/3 less than equal to x less than equal to 2/3, we can write fgx equal to fx times gx, and if we put the value, just see the function, then this value would be equal to 0. That means we can tell fg is identically 0 in this interval. That means fg belongs to the ideal J. Okay? Notice here f not belongs to J because here fx only 0 in the interval 0 to half, but in the question has given fx is identically 0 in the interval 1/3 to 2/3. So fx not belongs to the ideal J. Similarly, gx also not belongs to the ideal J because here only the function is 0 on the interval 1/2 to 2/3. So fg belongs to J, but neither f belongs to J nor g belongs to J. Okay? Are you getting? That means this ideal not be prime ideal. Okay? Now notice the second option. The second option is f belongs to C01 such that f of 1/3 equal to f of 2/3 equal to 0. And this solution is same like first solution. Here the point is fixed. Here 1/3 and 2/3. At that point the value of the function is 0. Same like first, consider f of 1/3 equal to 0, but f of 2/3 not equal to 0. Consider this type of function, and g of 1/3 not equal to 0 and g of 2/3 equal to 0. Now consider fg 1/3 equal to, we can write it as f of 1/3 times g of 1/3, and obviously this value would be 0. Similarly, fg 2/3 would be f of 2/3 times g of 2/3, and this value is equal to 0 obviously. That means from this condition we can tell obviously fg belongs to the ideal I. Sorry, here the ideal considered as J, but notice neither f belongs to J nor g belongs to J. Neither f belongs to J nor g belongs to J. Okay? That means obviously this ideal not be prime ideal. Same like before. Means option 2 also wrong option. And option 3, f belongs to C01 such that f of 1/3 equal to 0. And obviously this option is right option because I had seen in my earlier video in C01 this type of function obviously maximal ideal. And always in a commutative ring with unity, all maximal ideal be prime ideal. Since C01 is commutative ring with unity, obviously this ring is maximal ideal, so obviously that implies the ideal obviously be prime ideal. But here I will do one other method. Other way is consider f of 1/3 equal to A and g of 1/3 equal to B, which is different number. And to prove fg belongs to ideal, that means fg 1/3 would be 0. And that imply f of 1/3 times g of 1/3 equal to 0, which imply ab equal to 0. And from this line, since C01 is an integral domain, that means either a equal to 0 or b equal to 0. Therefore, obviously either f of 1/3 equal to 0 or g of 1/3 equal to 0. That means either f belongs to j or g belongs to j. Are you getting the proof? This is one type of proof. Okay. Type of question which had come in CSIR Net June 2019. The question is, let C01 be the ring of real valued continuous function on 01. Consider the set A equal to set of all function in C01 such that f of 1/3 equal to f of 3/4 equal to 0. Then which of the following statement are true? Option 1, A is an ideal in C01 but not prime ideal in C01. Option 2, A is prime ideal in C01. Option 3, A is a maximal ideal in C01. And option 4, A is a prime ideal in C01 but is not maximal ideal in C01. Obviously this ideal not be prime ideal in C01. So option 2 is a wrong option and option 4 also be wrong option. Here A is prime ideal but not maximal ideal. This is also wrong option. And option 3 also wrong option. This type of example to prove the maximal ideal, I have seen in my previous video. This type of ideal not be maximal ideal. Also other method, in a commutative ring with unity, every maximal ideal be prime ideal. If this ideal be maximal, then obviously this ideal be prime, but this ideal not be prime. So this option also wrong option. That means option 1 is a right option. A is an ideal in C01. I had proved in my earlier video this type of set obviously be an ideal in C01 but not prime ideal. Okay? Are you getting why I have told you this type of example are very important for any competitive exam? Now I will see one example which had come CSIR Net December 2019. The question is, I be an ideal of integer, then which of the following statements are true? Option 1, I is a principal ideal. Option 2, I is a prime ideal of integer. And option 3, if I is a prime ideal of integer, then I is maximal ideal of integer. And option 4, if I is a maximal ideal of integer, then I is a prime ideal of integer. This type of question is very easy. Just try to oneself at first. Here I be set of ideal of integer and then first option I is principal ideal. Obviously this is true which I had discussed in my previous video. Are you getting why I have told you my previous video is very important? Just recall, principal ideal means an ideal which is generated by single element. Then this is called principal ideal. Okay? And all ideal of integer be same as NZ type. So option 1 is a right option. Option 2 indicate I is a prime ideal of integer. For this, since in integer the ideal is look like NZ type, consider the ideal 6Z. And we all of us know that element 2 and 3 belongs to integer. Then their product mean 2 times t belongs to this ideal 6Z. But neither 2 belongs to 6Z nor 3 belongs to 6Z. Okay? From this line, we can tell easily the ideal 6Z is not prime ideal. And for this ideal, we can tell the option 2 is a wrong option. I is a prime ideal object. Not true. Option 3 indicate if I is a prime ideal of Z, then I is a maximal ideal object. For this, I will also consider one ideal. Consider I equal to 0 ideal. Then consider AB belongs to integer such that their product belongs to I. And from this line, we can tell AB equal to 0. That implies either A equal to 0 or B equal to 0. That means either A belongs to I or B belongs to I. That means the ideal 0 is obviously prime ideal. And this example also I have discussed in my earlier video elaborately. But we all of us know that 0 ideal be the smallest ideal of the ring. So 0 ideal cannot be maximal ideal. That means I have got an example which is prime ideal but not maximal ideal. Okay? Therefore, option 3 also be wrong option. Prime ideal, if I be prime ideal, then I is maximal ideal of integer. This is not true. And option 4 indicate if I is a maximal ideal of integer, then I is a prime ideal of integer. Obviously, this option is true. But why this option is true? Just see. We all of us know this theorem. In a commutative ring with unity, every maximal ideal be always prime ideal. Since here the ring Z is a commutative ring with unity 1, so obviously here every maximal ideal be prime ideal. Getting the idea? Okay. I will see existence of maximal ideal. R is a ring and I be a maximal ideal if and only if the quotient ring R mod I is a field. That means if we can find the quotient ring R mod I is a field, then obviously the ideal I be maximal ideal. And second, the 0 ideal of R is maximal. That imply obviously R is a field. The proof is look like if R is a field, that imply R contains exactly 2 ideals, 0 ideal and the ring itself. When the ideal 0 is maximal, then there is just no proper ideal. That means obviously the ring R is a field. That means 2 is obviously true. I will prove the option 1. Suppose I is a maximal ideal and we have to show the quotient ring R mod I is a field. And it is enough to show R mod I contains exactly 2 ideals. This will follow if we show that there are exactly 2 ideal of the ring R that contain I, and this is true obviously because the ideal I be maximal ideal. This is obviously true because the ideal contains I, that is maximal. This is one unit ideal and other ideal itself. Are you getting? So this result is obviously true. Now I will see one example about this topic. The ideal A such that f of 0 equal to 0 in the ring C01, where C01 is the set of all continuous function on the interval 01, we have to prove I is a maximal ideal. To prove I is a maximal ideal, we have to prove the quotient ring R mod I is a field. That means if we can to find the quotient ring R mod I is a field, then obviously the ideal I be maximal. To prove that, consider a mapping capital F from C01 to real number such that f of f equal to f of 0. Obviously this mapping is a ring homomorphism, and here the kernel of f equal to set of all f belongs to C01 such that capital FF equal to F0 equal to 0. Therefore, by first ring homomorphism theorem, we can tell easily F mod car F is isomorphic to the R, and since here R is a field, obviously this car F means this set obviously be maximal ideal. Are you getting the proof? Okay. And this example had come in N.b.h.m 2009 PhD exam. This type of exam actually very important for any competitive exam. Today I will stop here, but I will highly recommend you, please see this video with pay attention, because this video is very important for any competitive exam. See you soon. Stay safe and stay positive always. And don't forget to subscribe my channel and press like button. Thank you so much.